Today's video is going to be on net ionic equations. Okay, so far we've talked about double replacement reactions and how to predict the products of a double replacement reaction. But as I've been indicating to you, not all of the ions are actually taking part in that net ionic equation. Some of them are actually just kind of sitting there doing nothing. So what we need is an ionic equation or an equation that shows which ions are actually reacting together and actually performing the reaction. So net means that we're going to remove the stuff that's not actually doing anything. Okay, so we want to just kind of get rid of those ions that aren't doing anything and focus on the reaction, or the ions that take part in the double replacement reaction. And that's what a net ionic equation does. So remember, I've been trying to tell you that you want to represent, or well, when we represent this ionic compound with an AQ, what that means is you have a beaker with a solution, you got water here, and you have the ions dissolved and dissociated. Remember, those ions are now free to move around the solution. Okay, so if I have an ionic compound, AQ, we think of it as broken up into little ions that are free to move around the solution. Now, when we write our double replacement reactions, you've got to keep in mind what the reaction means. Okay, so when I mix these two solutions together and they're all in the same container, the outcome of that reaction is that sodium and nitrate remain aqueous, while the silver and the chloride are now forming a solid, and it kind of settles to the bottom. Now, the actual solid wouldn't be red; it technically would be white, and you'll see these in the labs that we're going to do pretty soon. Okay, so the silver chloride is a solid that formed. Now if you look over here, the silver ions were free to move around the solution. Chloride ions were free to move around the solution, so they were banging all around inside this beaker. The silver is banging around all over in this beaker, but now they're locked in that solid sediment that sits at the bottom of the reaction. Okay, it just sits there and it can't move around, so those ions are no longer moving throughout the solution. Okay, but if we look at sodium and nitrate, notice the nitrate, sodium, sodium, nitrate. It hasn't changed at all. It's almost as if they didn't do anything, because they didn't do anything. Okay, so those are referred to as spectator ions. And the word spectator means obviously to kind of watch. Now, these ions aren't really watching anything because they're ions and they don't have any eyes, but the idea is that they are sitting there doing nothing. They do not take part in the reaction. So what we want to do is we want to rewrite this double replacement reaction and get rid of those ions that aren't doing anything. So that nitrate and that sodium aren't doing anything. So the real reaction here is that we have a silver ion, which is aqueous, and it reacts with a chloride ion that is aqueous, and what it does is it produces silver chloride solid. And this would be my net ionic equation, because I removed all of those ions that don't do anything. So this is my net ionic equation. All right, now be careful now, because this, again, you have to be able to interpret balanced equations. This does not mean that I have silver by itself in any way, shape, or form, right? The silver, because it can't have a silver positive charge without having a negative charge to balance it out. What it is doing is it's just simply saying that between these two substances, that nitrate doesn't do anything. The sodium doesn't do anything. So I'm crossing them out, but they're still in that container. Just because I'm crossing them out in my balanced equation and not writing them in my net ionic equation doesn't mean that they're not there. Okay? So let's take a look at another example here. Let's take a look at lithium hydroxide, aqueous, reacting with iron nitrate, aqueous. And if you do the double replacement reaction and you switch the ions around, you're going to get the following balanced equation. Just have to put a 2 here to balance it. Okay, so I'm assuming you guys can do this at this point. If not, go back and practice those other worksheets and make sure you can do that, because if you can't do this part, you're not going to be able to do the net ionic equations. So what I've done again is I've represented things with these beakers and the ions. Okay, so that's the physical reaction that's actually occurring, is that I get that buildup of solid iron hydroxide. Now, you don't have to draw these beakers, and well, I didn't draw them, obviously they're pictures, but you don't have to go this step. What I would do is, in the beginning, what I tell students to do is take anything that is aqueous and ionic and rewrite it in its ion form. Now, one thing about balancing, by the way, since I'm going to write the net ionic equation, it really wasn't necessary to balance this. If I ask you for the net ionic equation, I would strongly recommend you wait and not balance the whole overall reaction, because you're going to need this to kind of see what forms the solid. Okay, so I'm going to write these out and I'm going to put them all in ions. So if I have lithium hydroxide. I'm going to skip writing the states of matter because this isn't my final reaction. I'm just breaking this up into ions. So I'm kind of representing this portion right here, but just not drawing the beakers. Iron ions and nitrate ions. And I'm not worrying about balancing right now. What I'm worrying about is just the net overall reaction. Iron, nitrate, aqueous, I write it in its ion forms. If I have ionic compound aqueous, I write it in its ion form. And it would be an ion. And over here I have nitrate. Now we get to that last one. Now, I don't have aqueous. So if it is not an aqueous description, if it's not an aqueous state of matter, I will not write it in ions. So I'm not going to write iron ions and hydroxide ions. I'm going to keep it as iron hydroxide solid because those ions are not free to move around solution. And that's important because that is going to be the driving force behind my reaction. That's what's causing the reaction to happen. Now, this is what's called a complete ionic equation. I just wrote everything in its ion form, okay, kind of representing this graph right here. Or say the picture's right there. Anyway, so what I do now is I go back and I look at my reaction and I say, what didn't change? Well, lithium stayed the same. My hydroxide went from an ion to now being locked in a solid. It's still an ion, but it's now in a solid phase, so its phase of states of matter changed. So I don't cross that off. I don't cross off the iron because that also changed along with the hydroxide. My nitrate cancels, right? So those are my spectator ions, the ones that aren't doing anything. So the overall reaction that I would write would be hydroxide, aqueous. Okay, this is going to be my net ionic equation because now I'm going to start following my rules. I'm going to balance things. I'm going to write the states of matter. Iron 2+, which would be aqueous. And I would have iron hydroxide. In this case, iron 2 hydroxide. And that would be a solid. Now, when it comes time for points and when I'm grading these, I will be grading this state of matter here. So I'm looking for that solid. So if I don't see the solid here, you didn't confirm to me that you know that this is a double replacement reaction. So I need to see solids at this point. This solid and liquid for water, which I'll show you in just a minute, are the ones that you definitely will need to have states of matter to be accurate. Okay. Other than that, states of matter I'm not going to grade as heavily. Okay. So that's the only place that I'm going to grade them for accuracy. All right. Now my net ionic equation is not finished because I have to put a 2 here because I need 2 hydroxides to balance out this formula. So this here is my net ionic equation for the production of iron hydroxide, okay, from this reaction. So again, what I've done is I write the full equation. I would recommend you skip the balancing. Okay, you can skip the balancing because I'm not asking for the excuse me, I'm not asking for the complete balanced equation. I'm just asking you for the net ionic equation. I would recommend that you then draw out all the ions that are present. Anything aqueous, put in ion form. Anything aqueous, put in ion form. Anything solids or liquids, you're going to keep together. You're not going to write as ions. Cross off the ions that don't change. Those are now your spectator ions. Rewrite what's left, okay, and then balance it. Notice it's a lot easier to balance this than it is to balance this. The problem is if you put a 2 here, then you got to put a 2 here and a 2 here and a 2 here. Excuse me. There's no sense in doing that because nitrates dropped out. Lithium's dropped out. Why bother balancing those things? Okay? All right, let's look at a couple more. And I'm going to make this go a little bit faster on these. I'm not going to draw the beakers and stuff, but I'm just going to start going right into the net ionic equation. All right, so we've got hydrochloric acid, barium hydroxide, barium chloride, and oh, look at this. HOH is formed because I take this and this goes together. This is my acid-base reaction, which we're going to talk about in the next video, which I'm pretty much talking about now. Anyway, so this over here is water. Remember, we write it traditionally as H2O. Again, if you want to write it as H2O, it's fine. But the key here is that you recognize that this forms a liquid. So state of matter I'm going to be grading would be water with a liquid on it. Okay, so make sure you got the liquid there and your formation of solids. You should recognize water is a molecule and it's removed the ions from solution. Okay, so what I'm going to do is I'm going to come back and anything that's aqueous, I'm going to write in its ion form. As long as it's a strong acid, okay, any acids and any bases you're going to deal with are going to be aqueous. Now you wouldn't recognize this as a base, but it is because of hydroxide, but you can recognize it as an ionic compound. So H plus Cl minus plus barium, which is a 2+, and my hydroxide, which is going to be OH minus. Again, I'm not worrying about balancing right now. I'm just writing the species out, or the ions that I have from each of the substances. Anything ionic, aqueous, acid aqueous will be written in ion form. So barium, 2 plus, chloride, again, don't worry about balancing right now, and then HOH. And I'm going to keep the liquid here just to remind myself. And I come back and I cross off the ions that aren't doing anything. Hydrogen goes from an ion to molecular water. Chloride doesn't do anything. Get rid of it. Barium doesn't do anything. Get rid of it. Hydroxide goes from an ion to molecular water. So my overall net equation is going to be H plus aqueous plus OH minus aqueous gives me HOH. Again, if you want to change that to water, you can, to H2O, but I like kind of keeping it that way. It's easy to balance the hydroxides. So HOH, HOH. Now notice here, I had a 2 here for that hydroxide. I didn't bother balancing it, and I don't need to, because it's balanced as it is. If you were to balance this equation, you would have a 2 here, a 2 here, and a 2 here, and you're going to reduce it down to its lowest form anyway. Okay? So again, balance at the very end of the net ionic equations. Okay? Unless I'm asking for the full equation. Okay? If I'm asking for that full balanced equation, then you would write the 2's here. All right, last one I'm going to do is tin 4 bromide, phosphoric acid, tin 4 phosphate, hydrobromic. Okay, so my tin 4 phosphate is the formation of the solid. I'm going to follow the same rules I just did. Anything aqueous ionic, I write in its ion form. Tin 4 plus bromide. This is a good way to practice and remind yourself what the charges are in each of the individual substances. Hydrogen ions, phosphate ions. Then you have tin phosphate, tin 4 phosphate, and that's my solid. So I'm going to keep that together, and then H plus and Br minus. Okay, I'm going to go through and get rid of my spectator ions. Anything that's not in here is a spectator ion, so H plus Br, H plus Br minus. So my overall net ionic equation is tin 4 plus phosphate gives me tin, whoops, let me write that again. Make it look nice and neat. Solid. And I forgot the AQs here. I'll just kind of throw them right here. AQ, AQ. All right, now I need to balance this. So to balance this, I need to put a 3 here, and I need a 4 here. And there is your balanced net ionic equation. Definitely a lot easier to balance this than it would be to balance the whole equation. Okay? One thing that students tend to notice, and this is one thing I'd be careful with, is they'll see this and go, oh, wait a minute, if this is forming the solid, couldn't I just do this backwards and do tin 3 plus, and 3 here, and then put a 4 here? Couldn't I just undo this? And I get this a lot. Students will write tin plus PO4. And then they'll throw the 3 here and the 4 here. Okay? What they typically forget is to put the charges on here. So just be careful if you're going to do any shortcuts. Yeah, I know there's a lot of ways to cut corners on these, but be very careful because these have to be ions for this to be a net ionic equation. Alright, so if you're going to do any shortcuts, just be careful. But that's net ionic equations, and I'll see you in class to answer questions.